Greetings, welcome to Let's Do It 7.26. In this LDI we're going to talk about the binomial probability distribution. So first thing that we need to know in the binomial probability distribution is the probability of success in a Bernoulli random variable. So if you don't remember what a Bernoulli random variable is, you might want to go back and rewatch the last part of the previous LDI. In LDI 7.24 we talked about what a Bernoulli random variable was. It's a variable where you have just two possible things that can happen, either success or failure. So what we're going to do is look at what this probability of success is. Now, one of the things that I want to let you know up front is that this probability of success is going to be a parameter, okay? It's a population value. And that's illustrated in our first example here. We have all possible people who are enrolled at this particular community college. We see that there are 500 freshmen, 274 sophomores, 191 juniors, and 154 seniors enrolled in this school. And what they want to know is that what is the probability of selecting a senior if that's defined to be a success, okay? A Bernoulli trial has one or two possible outcomes, either success or failure. It's dichotomous in the sense that it's one or it's the other. A success, all that means is we successfully found what we're looking for. So it's very important that we define up front what it is we're looking for. Well, we're looking to randomly select a student from this college and see if they're a senior. So what we want to know is what is our chances of that occurring. Well, to figure that out, we have to know how many students are actually going to the school. So you got 500 plus 274 plus stuff I can't do in my head because I'm not that great at arithmetic. So we'll go ahead and get out our calculator for this. So we've got 500 plus 274 plus 191 plus 154, okay? Hit an enter, and that tells us there's 1,119 students enrolled in this college. So what that tells me is that I've got 154 seniors out of the 1,119 possible students. So that's my probability of success. Now that said, probably not a bad idea to give that as a decimal in terms of percentages, because your viewing public typically is going to want that number as a decimal, okay? So that's 154 divided by 1,119, which comes out to be that we've got about a 13.8% chance, okay? So this number is approximately 13.8%, okay? All right, let's try the next one. We got a standard deck of cards containing 52 cards, 13 cards of each of the four suits. Four suits are spades, hearts, diamonds, and clubs. Each suit contains four face cards, which I don't completely agree with. I've always defined face cards as Jack, Queen, King, but Martha and Brenda decided it's Jack, Queen, King, and Ace, and 9 numbered cards from 2 through 10. The card is drawn from a well-shuffled standard deck of cards. A success is being defined as a face card. What is the probability of success? Again, muy importante is we've got to know what was the definition of being a success, and so that's a face card. So it's dichotomous in the sense that either you're a face card or you're not. And there's all this other stuff, information about the deck of cards. All we need to know is what is a face card and what is not. So there are 52 cards in the deck. There are 4 face cards in each suit, so 4 by 4 is 16. So that tells me the probability of success here is going to be 16 out of 52 on the first draw. Okay. Now again, not a bad idea to give your viewing public that number as a decimal. Okay, so you can turn it into a percentage. So we're going to take that and make that 16 divided by 52, which is about 30.8%. Okay, so that would be about 30.8% of the time you'll get a face card on your first draw. Okay, if a game consists of rolling 2 fair die, the success is defined as rolling doubles. What is the probability of success? Now, if you don't have it in front of you, you might want to go back and take a look. But there is that list of the game of craps of all the possible outcomes that can come in rolling a 2 fair die. And in there we'll see that there are 6 cases of doubles. So that's 636, which if you want to reduce that to 1/6, which is equal to 16.7%. Okay? All right, let's keep moving with this now. And let's talk about what we're doing here. what we're going to, or the big thing we want to get with all this business of combinations and probabilities of success and Bernoulli trials is what's referred to as the binomial probability distribution, or the binomial distribution. Very important probability distribution. It's a discrete distribution, and it's used a lot in the real world. A binomial random variable is the total number of successes in n independent Bernoulli trials, on which each trial the probability of success is p. We say x is binomial of n by p. So again, this is like our notation that we've had for uniform and normal, where the first letter tells us the type of distribution we're working in. In this case, the b stands for binomial, the n is the number of trials, and the p is the probability of success. Now, if you go to page 469 of your textbook, you'll see a huge amount of information about the binomial distribution there. Let's go ahead and take a look at part of that, and that's the calculating formula to actually calculate a binomial probability. Okay, so a binomial probability is the probability of success in a single trial, is what p is equal to. Q is the probability of failure in a single trial, n is the number of independent trials, and x is the number of successes in the n trials. Okay, now notice the formula here. It's made up of two basic pieces. The first piece right here, that's a counting tool. It's the number of subsets. It's the number of ways that the success can occur. And what this part of the notation is about is the probability in any one of those particular events of that occurring. Okay? All right, let's leave it there for just a second, and we'll come back to this formula in a minute, and let's set up a binomial trial so we can see how to actually use this thing. Let's say we have a situation where we're going to roll a fair die 5 times, okay? So roll a fair die 5 times, okay? And a success is a 3, okay? All right, so if the success is a 3, the first step in determining what's going on with this, whether it's a binomial distribution or not, is to decide whether or not it's each of the trials is dichotomous. So first thing to notice here is that the 5, that corresponds to my n. My n is equal to 5 here because I have 5 trials, okay? And now we say a success here is a 3. Now what we mean by that is that you can think about it as this way. As a success is I see this when I roll my die, okay? So if I get that, then I had a successful event. So what we know is the probability of that occurring, or the probability of success, theoretically, or from the model, would be 1/6, okay? So now based upon that, I can actually come up with probability calculations, all right? So what I'd like to know is what I'd like to find out is what is the probability that my random variable x takes on the value of, say, 2. All right. Well, what the heck is that? Let's see if we can define what that world I just wrote down there, what that means. Well, by doing that, what I'm saying is what I want to know. Let's go ahead and make my dice a little nicer here this time. What I'd like to know is I want to know the probability of, I rolled it 5 times, right? So we'll make it 5 little squares here to make my 5 die, okay? And 4, and then 1 more. There's my 5th die. Okay, so what I'm looking for is I want to have a situation where I want to know when x is exactly 2. Say I rolled this. Say this is the way my dice landed, okay? That would count as a success. That would count as meeting my requirement for x being equal to 2. Why is that? Well, because what the binomial random variable is doing here, and this is critical that you understand this part, is it's counting the number of successes in n trials. Okay? So what does x do? X counts the number of successes in n trials. Okay? All right. So in this case, it's how many times did I get a 3 when I rolled the die 5 times. All right, in this case, it would have returned a 2, would have been the answer there, okay? All right, so let's see if we can actually do the calculation of this probability here. So let's go back to the formula here for a second. Let me clean it all up and get all this nasty stuff out of the way. So what it says I need to do is I need to do n choose x Then take the probability of success, raise that to the x, take the probability of failure and raise that to the n minus x. All right? So the probability of x being equal to 2, okay? Let's go ahead and get rid of that. Come here, you. Hang on just a second here. I'll be right with you. I got to fix this here real quick. All right. So let's get rid of that question mark because I'm going to know what it is here in just a second. So what is it? Well, I have to go back to the formula for just a second and look and see what is it I'm putting in here. I got to put in the n, I got to put in the x, I got to put the p, I got to put in the q, right? Okay. So in our case, the n, well, the n was 5, right? The x that I'm working with, that's a 2, so that's 5 choose 2. The probability of success, well, that was 1/6, and that's supposed to be raised to the x, which is a 2. And then let's back up for just a second to this formula here. What about this value of q here? Well, the value of q is equal to 1 minus p. It's the probability of failure. It's the probability of not seeing what I wanted. In other words, anything but a 3, okay? And what's the probability of that happening? Well, that's going to happen 5/6 of the time. And let's see, what have I got here? I got a 2 from the total number of 5, so that's going to be a 3, okay? So how do I do that calculation on the calculator? Well, I'll do it once really quickly by hand, and then I'll show you how we'll do it using the distributions menu. So one time by hand, here we go. So let's clear that out, and I got to go 5, math, probability, number 3 for NCR, put in a 2. So that's the number of ways that this can happen, all right? And then times 1 divided by 6, close parenthesis, squared, times parenthesis 5 divided by 6, close the parentheses, to the third, okay? And enter, and it says that when I roll a fair die 5 times, I would expect to see a 3 in there twice in that set, about 16.1% of the time that's going to happen, okay? All right. So is there a better way of doing this? Oops, wrong way, sorry about that. Is there a better way of doing this other than the formula? Well, it turns out that there is. That formula right there is built into our calculator, as we would have suspected, okay? So let's do this problem one more time, but this time let's do it using the distributions menu, okay? So let's go ahead and clear out everything that's in there. Let's go second, distributions. This is a place where we had normal CDF. And if you scroll down far enough in your table here of possible things, you'll come, there's the BinoPDF, and it turns out that's the one we're going to want, okay? So hit an enter there. And the BinoPDF needs from you a couple of things. It needs to know n, which in our case was 5. It needs to know what p is, which is 1/6. And it needs to know the particular value that you're looking for. In this case, it was a 2. Hit an enter, and look at that. It gave us exactly the same answers when we did it by hand. Okay, now that's a lot to chew on in one little bite, so I'm going to stop it here, and we'll come back and talk more about the binomial probability distribution in the next LDI with more examples.